We've been talking about the science of hydraulics. Now it's time to talk a little bit about the art of hydraulics. And I tend to think that those two categories, we have too hard a wall between those two categories. This podcast that I've been doing, I've been talking to a lot of like older, retired or retirement age hydraulic engineers or river engineers. And one of the themes that's come up from a lot of them is that they tend to see really concrete thinkers, people who came up through engineering curriculums, not last long in hydraulics. They realize that there's a lot of ambiguity in hydraulics and river engineering, and they tended to enjoy the engineering manuals in their engineering curriculum, and they go elsewhere. They go to design, they go to project management. The people who stay with hydraulics are the ones that actually have it's not so much a discipline as a temperament to have a little bit of comfort with ambiguity. And you would think that in hydraulics, we have the most beautiful equations, right? Cam just showed them to you, and we haven't even started talking about the St. Venant equations. Our equations are self-correcting. Are you kidding me? How lucky is that? If you just put the boundary condition a long ways downstream from your area of interest, it doesn't matter how wrong you get it, because it's going to be self-correcting by the time you get to your area of interest. They're beautiful equations. And so we tend to sometimes look down at, those hydrologists with all their free parameters and, the sediment transport people, what are they even doing, right? Like that's witchcraft. The groundwater modelers, they can't even see all their parameters. We have these beautiful, elegant equations. Except do we? We take all of our uncertainty and we put it all in one closet, right? It's like when my kids clean their room, one of my kids will actually go and put everything where it belongs, and another kid will just take everything and shove it under her bed, right? And that's what we do. We take all of our uncertainty and we shove it under our bed, and that bed is called the Manning's N parameter. Everything that we don't know, we just put into the Manning's N parameter. So part of the kind of melding between art and science that you're going to have to do as a hydraulic modeler is, you're going to use these gorgeous self-correcting equations, and they're going to do great. And then you're just going to infect them with all sorts of human intuition by choosing a Manning's N parameter. And that's why we kind of dedicate our whole talk in what is an engineering class with this more intuitive, more felt, more artistic sense of where am I going to come up with this Manning's N parameter. And so this is the resistance to flow talk. And so we're going to talk about the flow resistance equations. We're going to just talk a little bit about how this parameter fits into our beautiful equations. And then we'll talk about the factors that affect this, just so you know kind of what you're looking for. Then we'll talk about how to determine these. There's three main ways to determine these: charts, pictures, and equations. There's actually two other ways that I'll talk about, but those are the standards. And then we'll talk a little bit about, where do these go in RAS, and how can you play around with them in RAS to make them a little bit more responsive to what your river is actually doing. Okay, so first, the flow resistance equations. There are two flow resistance equations. You can use either of them in RAS. There's the HEC equation and the Manning's equation. These have two major differences. What are they? The Manning's coefficient, what's different about it? Okay, but the HEC has a HEC coefficient, right? So what's the difference between the Manning's and the HEC coefficient? Right. One is direct and one is inverse, right? And so as the Manning's N increases, velocity decreases, and vice versa for HEC. As HEC increases, the velocity increases. All right. What's the other difference? Don't worry about the 1.48. That drops to 1 when you use reasonable units like SI.
It's the exponent on R.
It's the exponent on R. The exponent on R. So there's two differences. One is that Manning's is inversely related to the empirical coefficient, and the other is that we have an extra R to the 1/6 in the Manning's equation. What? Well, that seems obscure. Okay, another question. I just learned this morning, so there's no reason you should know this. Which of these came first? That's what I thought. I thought the Manning's equation came first, and then the fancy Europeans came along with Shizzy, right? It sounds French. It sounds fancy, right? Like something you would get at Mishka's. I give me the Shizzy. Shizzy's equation was actually like 100 years before Manning's equation. So why is the more elegant equation earlier? Well, because it's more elegant, right? And so why is it more elegant? Well, the units. What do the units work out to? Well, the units of the coefficient are actually non-absurd. It's meters to the it's length to the 1/2 over seconds. It's not a unitless coefficient, but those are non-absurd units. What are the units of Manning's N? I don't know. There's a 1/6 in there. It's bizarre. It's weird. The units don't make any sense. But what happened is data. There's a 3-page footnote in Chow's Open Channel Hydraulics that basically explains the process. Is that Manning was an engineer who used Shizzy's equation and just found that it didn't fit the data. And so Manning went and he didn't do a dimensional analysis. He just fit the data and found that the extra 1/6 fit better. And that's actually why Manning's equation has won, at least in the United States. We use Manning's equation. It just tends to fit the data better. That also might be a founder effect. It might be a historical artifact, but that's why we do it. But what you need to know is that if you ever use Shizzy equation, I never have, but if you're working with stakeholders that want the Shizzy equation, the main thing you need to know is that there's going to be a different sensitivity to R, and the Shizzy equation is directly rather than inversely proportional. Okay, that's the last we're going to talk about Shizzy because we use Manning. Okay, so where does Manning's N fit in the equations that were presented to you yesterday? Well, it does not, right? You never saw an N. No one ever presented you an N when you talked about the energy equation yesterday. We don't care about Manning's equation. We care about the friction slope. The friction slope is the slope of what? I'm going to draw until someone answers. So this might get complicated. The energy grade line, thank you. So HF is the loss of energy between our computational nodes, which in this case are our cross sections, and SF is the slope of the energy grade line. Where does that come from? Where does SF come from? How do we compute that? Well, you'll notice that there is an S in Manning's equation. That's actually what we solve for, because we iterate on the velocity based on the depth. We iterate on the depth and the velocity, and we solve for the friction slope. And so the friction slope, this loss, which is what we're actually solving for, right? Because we are doing a backwater analysis where we're computing the loss between these. This is what we want, and this is really just the friction slope times this. We get the friction slope from Manning's equation, from the conveyance equation. The friction slope is flow divided by conveyance squared. What is conveyance? It's a weird idea. Conveyance is a weird idea. What conveyance really is Manning's equation minus the slope component times area. And so it is this kind of conceptual idea of what is the capacity to move flow before you add the driving force, which is the friction slope. But if you just kind of say conveyance is Manning's equation without the friction slope, then the friction slope by definition is the flow over the conveyance squared. And so that's how we do this. That's where Manning's equation fits in. And so if you kind of step back from the convoluted what is conveyance explanation, the answer is the friction slope, the loss of energy grade, is a function of what? The resistance to flow on the bed, which we quantify with what? Manning's N. And so that's where, now it's turtles all the way down, right? That's kind of how we got here. We're going to use Manning's N to compute the friction slope, which gives us our loss. Okay, so that's how we're going to use it.
Wait, can you
Yes?
say again what conveyance is?
Conveyance is weird. Who learned about conveyance? Did anyone else learn about conveyance? I didn't. Because it's not a thing. All right, conveyance is not a thing. Manning's equation can solve for V or for Q, right? If you wanted to solve for Q, what do? You multiply everything by A, right? Okay, so multiply everything by A, just put an A in there, and now you've got Manning's equation in terms of Q. Okay, what's the driving force of Manning's equation? I always think about equations like, what's doing the work? What's the engine here? And that's partially because I'm in sediment transport and I just, like, the engines are weird. But what's the engine here? What's the driving force? It's the slope, right? None of these other things are driving anything. Actually, it's like driving forces versus resisting forces, right? And then the resisting forces propagate through this. And so what's the driving force? It's the slope. So in a sense, conveyance is Manning's equation minus the driving force. It's the non-driving force portion of Manning's equation, which means essentially it's a flow potential. Right? It's the flow potential that you then multiply the slope by to scale the actual flow potential into flow. Yeah.
Yeah, so, I mean, the way I've been thinking of it is, I mean, I just started Googling it yesterday.
Okay.
Right, so tell me if I'm close. So it's basically the ability of a channel to carry water for a given slope.
That's right.
Yeah, because, so like, for instance, if you have the same cross-section, but it's very shallow, that would be a lower conveyance
Yep.
because you've got more wetted perimeter.
That's
than
right.
If you had like a semicircular channel.
That's right. And so if you think about a unit slope, how many slopes do you have? Well, I have one, I have two, I have three. All right, let's just take a unit slope. Conveyance is the ability for your channel to move water given the unit slope. You know, if I multiply this now by 2, I'm going to get twice as much flow. And so it's a little bit of a area minus resisting forces, and then I'm going to apply my slope to it to scale up to flow. But it's not a real thing. It's more of a numerical trick to isolate the friction slope in our equation. It's Manning's equation minus the friction slope. What affects Manning's N? When you're going to walk out into the field and try to estimate a Manning's N, what affects it? Well, the first thing that affects it, obviously, is the surface roughness. But we're already in trouble here. Because what actually is the surface roughness? Now you're in my world. Welcome to sediment transport. What actually causes roughness what sediment characteristics actually cause roughness?
Size.
The size of the sediment, right? If you've got cobbles, you're going to get more roughness than gravel. Are you going to get more roughness than sand?
No.
No, why not? Why would sand give you more roughness than gravel?
Is it because of that?
Yes! Sand self-organizes into waves, and so sand has emerging roughness properties, right? And so gravel and cobble transport like 1 grain at a time, but sand turns into bed forms. And the roughness of an individual sand grain is almost insignificant, but they self-organize into these waves, and now these waves are a foot. In the Mississippi, they're 30 feet. In the Paraná, they're 45. Like, those are significant roughness elements that you have to contend with. So the surface roughness, whether it's the material itself or the bed forms is what we call them, are kind of, we call that the kind of base grain roughness. But then you have to add things like vegetation, right? And vegetation has possible seasonal effects. Right? I remember I was doing one of my first studies, again, University of Wisconsin, was we were modeling this channel, and this channel was like choked with macrophytes. And so we did a little backwater calculation, but the roughness was off the charts because you had all this drag from the macrophytes that were taking up like 10%, 20% of the area of the channel. And so we do have seasonal N values in RAS for that purpose. Channel irregularities and sinuosity. Remember, the thing you have to remember about Manning's N value is we talk about it as roughness. But it's the closet, or I guess the bed was the metaphor I used. It's the bed that we're sweeping all of our uncertainty under. And so if you think about a sinuous channel, where is the energy going in a bend? Well, you get all of these helical flow effects. Things that we don't even get in a two-dimensional model, and to be honest, three-dimensional models aren't very good at them. And so you have all of these energy losses in a sinuous channel. The more sinuous your channel is, the more losses you're going to have. Is that channel roughness? It's not. Where else are we going to put it? We put it in the Manning's N. Scour and deposition. You don't just lose energy based on the roughness of the roughness elements, but if the channel is actually scouring or depositing, you're doing work, and work takes energy. And so that can also play into it. Obstructions, this is again, when we talk about our beautiful equations, you're going to get, 6 hours of excellent bridge content. It's excellent. You're going to love it. It's gonna change your life. And it's so elegant. These equations are so beautiful. And one of the things that we're not even going to mention is the fact that almost every flood, your bridge is going to get choked with debris. And you're going to have to figure out how to account for that debris in your backwater analysis. The Truckee River study that Alex showed at the end, that was my first big study when I came to HEC. And that was my calibration, which is why we'll talk about it. And I can tell you that calibration wasn't even close until I put debris on my bridges. And yes, you can do that in RAS, but you're going to have to account for it. And it doesn't just happen in bridges, though. Like, debris catches, throughout your system, and a healthy system has active wood in it, right? And so you're going to have to account for that. Temperature. Temperature is going to affect Manning's N value. Okay, before I show this, what do you think? We have Omaha District here, and we have, do we have Alaska District? All right, Alaska District. Where do you think temperature is more likely to affect N value? In the Omaha District or in the Alaska District? Omaha District has the Missouri River and some pretty good temperature changes. The Alaska District has the most temperature changes and largely gravel and cobble bed rivers. It's actually the Omaha District. And it's because, why? Someone who voted for Omaha. Why is Omaha going to be more, the N value in Omaha going to be more susceptible to temperature? That's exactly right. And what kind of sediment are we carrying in the Missouri River? Yeah, mainly fine sand. And so think about this. In the Alaska District, you're carrying mostly cobbles and boulders, which means that what does temperature do to the water? It changes the viscosity of the water, which changes the ability of the water to move sediment. But how much does it really change the ability to move cobbles and boulders? Not much at all. You can make the water more viscous, and a cobble or a boulder won't move much differently, unless you get ice, and then ice can move cobbles and boulders, but that's a different thing. But and that's because in gravel bed rivers, the roughness element is the boulder itself, the cobble itself. In the Missouri River, the roughness element is the bed forms because of the sand. And so as temperature decreases, the bed forms actually plane out because you've got more shear stress, because the water is, I'm going to say heavier, that's not right? But the water is denser, and so the bed forms actually, the amplitude of the bed forms drops in response to the increased shear stress of the more dense water. And so this is a classic, from the Omaha District, this is a classic plot of, you've got temperature dropping and you've got Manning's N value dropping. And so the Manning's N value actually drops through the winter and then comes back up in the summer. All right, so how are we going to figure these things out? How are we going to determine our Manning's N value? We have 3 that we're going to talk about, but there's 2 others I want to talk about, and one we're just going to start with. You are not going to estimate your Manning's N value. I mean, you are, but if that's all you do and the report comes to me, it's not going to go well in review. Uncertain parameters must be, finish the sentence. calibrated, right? If you have uncertain parameters, you need to calibrate them, especially if they're uncertain plus or minus 30%. And so how are you actually going to develop your Manning's N values? You're going to calibrate them, which means you're going to need high water marks, which means every time you have an event, you should be sending interns out to the field to survey trash lines. Like, this just needs to be common practice, because you know that if you have an event, someone's going to come to you in 2 years and ask you to model it. And this just has to be part of district culture. So this is what I did in the Buffalo district. You know, I'm not sure Paul Morawski's still there, but you know, Paul would come over to my office like, we just had a flood down in Casanova. Go shoot the trash lines, and that's how you build. That's how you build this infrastructure to be able to do these models. Okay, so I'm going to tell you a bunch of stuff, and none of it's true. This is the stuff I'm going to tell you is how you get your first guess, but then you got to calibrate it. Okay, but one of the problems with calibration is that you can get outrageous numbers because there's another problem in your model, that's called equifinality. And so you want to also have good intuition about these to know what's the range I can calibrate in, what's a good initial value. And so where do we get that? Well, there are three options: lookup tables, photographic comparison, and analytical equations. So lookup tables, I don't have a lot to say about that, except we have them in RAS, right? And so there are lookup, these all come from Chow, open channel hydraulics text, and you'll notice 0.6 plus or minus 0.2 is the level of detail you're going to get from these. I don't find these very useful for natural systems. Where I do find these useful is for engineered systems. You know, over here, concrete, float finish, unfit. I don't know what any of these words mean, but there's a structural engineer in your office who could help. But these have a much more bounded range, and really what I'm looking for is the upper bound, because I always choose N values that are far too high for engineered systems. So I find that a lot more useful. Where do you get to these tables? If you don't have Chow because it's limited edition, you'll find that anywhere in RAS that you have this question mark, we will send you to the appropriate portion of the RAS manual. Okay, you guys heard about F1? Has anyone told you about F1? No, this is why you come to the class. These are the pro tips, the Easter eggs. Okay, so yes, you can push this question mark anywhere you see one, but what if there's not a question mark? If you are anywhere in RAS and you push F1, we will take you to if you're online, we will take you to the appropriate place in the user's manual. And that is just we call that context-specific help. This is why we actually put all of our user documentation online. And so that should just kind of become a standard practice, because the user's manual is phenomenal. It's phenomenal, but it's too big, right? Like, I don't even know where to start. And so that context-specific help is really that's the workflow that you want to use to find the right documentation. Okay, so charts. The next thing that has historically been part of what we do is photographic comparison. There are a number of sites out there where they show you calibrated N values, and you compare your system to them. All right, so we're going to play a game. We're going to play a guess that N value game. All right, if you all shout it out, then none of you will be complicit in the answer. Give me some N values for this. I'll give you a hint. These are going to increase. All right, so each N value will be higher than the last one. That doesn't help you with this one, but let me hear some N values. What do you think?
0.02.
Sorry, for the channel.
0.027.
I'm glad I'm only hearing 2 sig figs. So I'll give you this bit now. When I review projects, which I do, they come to HEC. I figured out that there is a psychology of review. In the first 8 minutes, I either develop a skeptical or a generous point of view. And that really comes from like 5 or 6 things that I check first off. And those are things like, are any of your water surface profiles crossing? How are you using it in effective flow areas? What is your bridge? What have you selected an appropriate bridge algorithm? And I have to tell you, this one's not fair, but how many sig figs have you used to define your n value? If your n value is defined to 5 sig figs, I'm immediately skeptical. It's gonna affect the entire review. You cannot know an n value to more than 2 sig figs, maybe 3 if you're calibrating, but like, okay, anyway, there's that bit. Okay, this is 0.026, 0.026. A lot of people are pretty close. This is, why is it 0.026? Well,
It said
no,
0.025.
this is the first time I've tried to do this interactively, because this is so boring for me to just do straight up. Why is this 0.026? That's really low, incidentally. That's about as low as you go for a natural channel. Well, look how straight it is. There's no sinuosity. There's no debris. You've got a clay to silt bed, but there's no bed forms because it's incised. And so this is about as close to an engineered system as a natural system's going to get. Okay. Shout them out.
0.046.
All right. He had no cover. None of you just left him hanging.
0.047.
It's a prices right. You just got prices rated. This is 0.028. Now, I think that's surprising to me. Now, this is actually true because these are calibrated, but this is actually a big river. These are actually small roughness elements for this river. The river is straight, and it's conveying. I actually think that number feels very low, but it did calibrate, and this is helpful for building our framework. Okay, what do you think? Oh, 0.035. My favorite n value. My favorite n value, 0.035. 0.05.
0.046.
All right, we have covered the range. This is very close to my favorite n value. And this is actually how they came up with it. This is a USGS. We actually used to have a direct link to this in RAS. Now I think you have to go to the manual to find the link. But the USGS, this is on the website. And this is, if I don't know, I start with 0.035. You've got some roughness elements. You've got some sinuosity. It's a moderately sized channel compared to the roughness elements. This is average, basically. This is an average river. All right. Go for it.
0.04.
Is there ice?
That's a great question. No, not right now. Incidentally, what a great question. Because if there's ice, what happens? You actually need 2 Manning's n values. Why? Yeah, you actually need a Manning's n value for the ice itself because you've actually got two roughness surfaces. And that's different. If you have an ice cover, it's like 0.02. But if it's an ice jam, it's like 0.045. And so that's actually a really big deal. Sorry, I digress. Anytime, I'm very distractible. Squirrel. What's that? Okay. Nice. 0.3. Look at that. Yeah, and so this is my basic framework. If the river is average, it's a Lake Wobegon River. It's about 0.035. If you get kind of higher gradient with bigger roughness elements, and generally you're going up into the mountains a little bit, you're going to start to get into the 0.04s and 0.05s. If you go down gradient into like the Missouris and the Mississippis, and you start getting below the 0.03s is kind of the way I think about this. Okay, let's do a couple more. All right, now we're farther, yeah.
I have a question
Yeah.
about these n values. Is this just an average n value for the entire system?
For the reach. So basically what they do is they took 3 cross sections, and they didn't use RAS because it was pre-RAS, but they basically did exactly what RAS does and calibrated the n value to those 3 cross sections, which
Okay.
is part of why these are all straight reaches. But you're going to do the same thing, right? I remember the first time I learned RAS in grad school, And I remember the Professor Hoops. No, all right. Professor Hoops took us out, and we took our cross sections, and then he asked me to come up with a roughness for that, and I was like, well, the roughness for that or the roughness for that, because it's very different, right? So you are going to have to do this like artistic conceptual integration. All right. Let's do one more, and then there it is. Okay.
0.057.
Thank you. Yes, good, good. The first time I had to use a 0.05, I felt like I was cheating. I felt like it was wrong. But you get up into high gradient systems in the mountains, 0.05s are pretty common. 0.06s, not so much, but you can run into them in high gradient systems. And then, maybe, yeah, I guess that's the high bound. That's the high bound for a channel. Of course, overbanks are a totally different story. Overbanks, 0.07 is kind of where you start, unless it's an urban system. An urban system, can be 0.03 if it's a parking lot, but like if you've got houses and you're accounting for the houses, it actually gets up to 0.07, 0.08, 0.1 pretty quickly in your overbanks. Which is more sensitive, your N value in your channel or your N value in your overbanks? It is channel. Why is it channel? Because you have
flow.
Yeah, I would say because you have more conveyance, but flow is actually the right answer. Yeah, the channel, and it's because it has the lower N value. You have more area. This is why conveyance is a thing, right? You have more area of flow in your overbank, but you have more conveyance in your channel. And the higher conveyance channel is going to be more sensitive to the N value. Okay.
So the point you were talking about with the block obstructions or the houses.
Yeah.
So if you're accounting for those already in your model by using block obstructions, do you still have to account for them with your N value?
This is a great question, and a question that you might want to ask each of us, because I think you might get different answers on the RAS team. For sure. The question is, if you use blocked obstructions to model the houses in your model, do you have to account for them in the Manning's N value? The question is, what are you trying to do with your Manning's N value, right? The weird thing is, if you don't do this, and incidentally, I'm going to suggest that you don't, then you're actually using your Manning's N value to remove conveyance. Do you see that? There are two ways to model this. One is you put in your houses, and then these are streets, right, which are going to have a Manning's N value of 0.02, but there's actually going to be some turbulence and some weird things going on here, so we'll use an N value of 0.03 here. And you're going to have roughness at the edge of your buildings, and that's going to kind of work out. Or you can do a floodplain like this and just use an N value of 0.07 and get the same answer. So what you're doing actually is you're saying, actually, N and A, those are both in Manning's equations. I'm just trying to get an SF. And so I'm actually going to use N to remove A. That's what you're doing here. So this is more correct. I like this better. I'm going to give the calibration talk on Thursday, and I have very strong thoughts on calibration, most of which you won't get until you come to the sediment class. Then you'll get them all. But because of what's called the equifinality trap, I try to minimize my free parameters. This actually has two free parameters in it, because those are the houses you have at that cross section, but is that a really good integration of the houses that you have throughout the system? And are those houses filling with water, or are they not? And what kind of inner-house turbulence are you getting? And what about cars? And is this do you really trust this representation of reality? In general, I like to go with a simpler representation of reality in a simpler model. So the answer to your question is yes, but I tend not to do it. I tend to do this instead. All right, the last thing is analytical equations. There are equations to come up with Manning's N values. I inherited this material And so I'm going to show you Cohen's method, even though I think it's a little bit silly. This is not really an equation. This is more of a conceptual model. And the idea behind Cohen's method is you want to think about what are all of the components that are adding resistance to flow into your system. And then you come up, because the n value is linear, these are additive, except for Cohen thinks that the meandering is a correction factor that should be applied to all of them. This is actually not a bad exercise to sit down with your team and do to come up with your initial Manning's n value. I find that I actually don't have any intuitive sense for any of these. And so it's part of the history of the field, and so we'll talk a little bit about it, but I don't tend to do this or see it in core reports. The Limerinos equation is something that I use. The Limerinos equation uses two variables, the hydraulic radius and the D84. So those of you who took a geotech class might remember what the D84 is. That's basically you line up all of the particles from smallest to largest, as if you were in elementary school, and then you take the 84th percentile particle. Which, why 84? Does anyone know? That's a weird number. 2 standard deviations above the mean, right? And usually we're like, well, that's silly, and that's why you sometimes see the D85, is because 84 just seems silly and, you know, kind of like statistical snobbery. But it is 2 standard deviations above the mean. So basically, you're coming up with a roughness based on the grain size of the material. So this should work well in sandbed rivers or cobble rivers. Cobble, why? That's right. It's not the particles themselves in a sandbed aren't what are giving you the roughness, right? You can find the 85th percentile sand particle, but those are going to self-organize into dunes. And so this won't actually give you the n value for a sandbed. But I tell you, I've used this in gravel bed flumes, and it's been right to 3 sig figs. And so this is really good for cobble bed systems or especially flume work. Jarrett's equation is messier. Anytime you see coefficients like that, like this, what does it mean? Yeah, like no one did dimensional analysis to come up with those coefficients. And what they did is they just plotted a bunch of data and then they tested the significance of different independent variables, and then they fit a curve. And so Jarrett's equation is very empirical, and whenever something's empirical, that means it's very site-specific, right? It matters where these data came from. And so where did these data come from? Mountain rivers in Colorado. It was like 56 mountain rivers in Colorado, which is awesome because that was actually a data gap. Most of the n value work had been done in these like kind of large lowland rivers. So if you're doing mountain rivers anywhere, I've used this in the Sierra, it's really great. These numbers come out really high, and they turn out to be right. And so I remember the first time I used an n value of 0.056. That's what calibrated, and I was very uncomfortable with it. I went to Gary Bruner, who was here at the time, and he said, well, what does Jarrett's equation tell you? It's a mountainous river. I was like, what's Jarrett's equation? So I went and I ran Jarrett's equation, and Jarrett's equation came out 0.058. He's like, well, now you have multiple attestations to your n value against your intuition, and your intuition is wrong because you don't know what you're doing. And so, sorry. That might have actually been an accurate representation of that conversation. My calibration says 0.056. Jarrett's equation says 0.058. Now I have more trust of something that's kind of outside of my intuition experience. Brownlee it's in our manuals. We don't use it that much. I'd love to just put a calculator in RAS to help you come up with this because these parameters are weird. It's based on the D50. But it's also based on the spread of the data. And what Brownlee said is, using the actual grain size alone is not appropriate for sandbed rivers. And so so this equation actually accounts for bed forms. And so the n value that the Brownlee equation computes is for sandbed rivers, but it's not computing it based on the grain size, but based on the bed form size that's expected. It is difficult, however. The supporting information's there. I think that we should probably come up with a calculator in RAS to help you come up with this. Okay, so that's how you come up with the n values. Although I told you that I had there were actually 5 methods. Here's the 5th one. You got to find a local mentor. Anytime you can get on a field visit, do it. And just, find the person who's been there the longest and just kind of put yourself in close proximity and start asking questions. Just ask them what they're looking at and just say, hey, if you had to choose, even if it's not the topic of conversation, say, if you had to choose an N value for this stream, what would it be? Finding a mentor is actually harder than it seems. I talk to a lot of students, and a lot of students find that they're actually very frustrating that the people that they want to mentor them are actually in demand. Like, there are people that they could have mentor them, but they're not the people they want, right? But the thing that makes someone a good mentor is that everyone wants their time. And so you need to be a little persistent. The protege needs to be persistent with the mentor. You can't expect a mentor to just take you on and lead you. You actually have to insert yourself a little bit, which means get on the teams, get on the field trips, and then just ask the questions. And I think you'll find that once you show legitimate interest in a mentor, they'll start to open up and they'll start to recognize, oh, this person asks good questions, and they'll start to see you as a protege, and that's when the flywheel of mentorship begins. Okay, that's not on my slide. Okay, so you have an N value. How do you put them in RAS? Well, we have standard, you have the channel N value, and then you have the 2 overbank N values, and that's easy, right? But then there are all of these other intricacies and nuances that we've talked about. Well, let's talk about a few of the other intricacies as well. There's actually a 3rd way to define roughness. There was a thinking early in the 20th century that wouldn't it be nice if we weren't actually talking about this empirical parameter, but that it was actually something you could measure. This actually comes from material sciences. I think the pipe people use this. And the idea is, what if we had an equivalent roughness height value? And so you can actually go out and measure what is the height of your roughness element. You can already start to see problems with this because we've already talked about all of the uncertainty we put in the N value that isn't just the height of your roughness element. But this was a popular way of thinking, and so the idea is that you can actually go in and put these K values into RAS. What we'll do with these K values, these roughness height element heights, we'll turn them into an N value. There is an equation for turning K, or we'll even turn them into a Shazy value. And so that's what we're going to do with them. But a lot of times this comes down to stakeholder comfort. I find that a lot of times you'll be dealing with a local stakeholder who just had a very particular education at a very particular university, and it has a very particular sense of what's right. And I find that in general, if I can say, sure, we'll do that, everything goes well. You don't want to fight the other scientists in the stakeholder teams. And so if they want to use a K value, sure, let's do it. It is more common for engineered materials, though, because in engineered materials you're often using pretty straight channels without a lot of debris, hopefully, or sinuosity, and so a lot of the roughness does come from the roughness element. And so these are actually in feet, which is hilarious to me. This is actually gets down to kind of machine precision of what is the actual distance of the roughness, and then we'll turn that into an N value based on equations. Okay, so this is where you put N values into RAS. You get a left overbank, a channel, and a right overbank N value. But what if you want more than 3? I often don't. Just to be honest, I often don't. I often think that really detailed N values are overspecified. I don't know my N value plus or minus 20%, and so the fact that I can put in more than 3 isn't super helpful to me. But you can, and so what you do is you ask for a horizontal variation in N value. I'll show you how to do that in a minute. And then instead of just getting 3, you go in and you put in an n value every time it changes. Now this can be a little bit weird because it feels like maybe you want to fill in all this space. You don't have to. It's just every time the n value changes from left bank to right bank, you put in the change. And then you can have as many as you want. Don't. Right? Like I see a lot of models with these that have 20 n values across them. And I just think you don't need that. You don't know that. Let's keep it as simple as possible. Then you have vertical, yeah.
Does that auto-populate if you use, yesterday during the workshop, they showed us a method to input n manually from
Yes.
the NLCD cover? So that will just...
Yes, and I'm going to show you that. You're anticipating something as well. I'm going to show you that in the little demo here. But this is how it comes in from Mapper. So if you were just bringing your n values from Mapper, which more and more is becoming the way to do it, even if you only have 3, it'll come in like this. And you can just leave it like that. That's fine. I'm going to show you actually how to convert it back if you want. That's better done in a demo than on a slide, though. Yeah, great question. You can also do vertical variations in n value. What if you have these kind of interesting islands that change n value at different depths? Really strange things are going on with your depth, with relationships, things like that. The vertical variations in n value is very data hungry. And you can essentially make a matrix between water surface elevation and river station. And you can change your n values in a very detailed way. We don't tend to do this. I've only used this once. It was on the Missouri in Gavin's Point, where the bars of the reservoir deposition, as you got higher water surface, the vegetation flattened, and you got a different n value. That's the only time I've ever used it, because the n value change was only in a very specific island. It wasn't across the whole cross section. And so if you have n value changes with water surface elevation in a specific part of your cross section, you can use this vertical variation with n value. But we almost never do because it's very data intensive. It's just incredibly tedious. So,
Thinking more of this situation actually.
oh, right here.
Yeah. Where there's a high point in the split channel.
So you can see that in this model, they actually did put in an n value for the channel, and then they actually have an n value for the bank for this part, which I do sometimes see, which I'm not against, because that actually is often a very different n value. And then they have another n value for this transition, which I probably wouldn't have done. If I was reviewing this model and you said, hey, this is vegetated, this has a separate n value, and you put in a separate n value, I wouldn't balk at that. I would say, oh, that probably is true. It might not be necessary because, again, you're outside, you're in this floodplain conveyance, velocity is low, it's going to be very insensitive to that result. But also, if I knew vegetation was there and you didn't put in a separate n value, I wouldn't balk at that either, because you're just lumping all of that together is fine. And the reason that we don't use the vertical variation n value unless you have a very specific part of your cross section that's doing weird things is because we almost always do use what we call the flow roughness factor. I usually use particles here, but Ken asked us about rigid fictional plants. So let's use Ken's rigid fictional plants. I just did it. The podcast is coming out on Friday is with Joanna Curran from the Seattle district, and she did a bunch of flume work with rigid fictional plants that actually didn't turn out to be rigid. They actually bent over like actually rigid plants do. But let's consider these rigid fictional plants. I won't make them green because they're fictional. So I'll make them purple because plants don't behave like this. But do they produce the same n value for this water surface elevation or this water surface elevation? Let's say that this calibrates to n equals 0.39. what n value, should this n value be higher, lower, or push? Give me a thumb. Higher, lower, or push? I'm just looking for participation. I'm not evaluating any thumbs. I'm going to do the Caesar here. It's going to be lower. Why? If I was to estimate, I would estimate something like that. Again, this is all fictional. These plants are fictional. These n values are fictional. But trend-wise, this tends to be where things go. Why? Well, because the roughness element is a larger percentage of the flow field. And so it's just acting on the flow more. And the Manning's n isn't physics. This is an empirical parameter. So stuff like this ends up mattering. And so I actually had a look. Oh, sorry. I need an O in there. These are way too high. Sorry. Order of magnitude. I had a little bit of a debate with a professor about whether this is true in 2D as well. The professor says, hey, if you did that in 2D, all this would go away. And now we started doing 2D modeling, and it's not true, which is why we actually do variation of n value with flow in 2D now, too. But basically, you've got all of this shedding going on here and shedding around these. This is where your roughness is coming from. And you've actually got a very small portion of the water surface here that isn't affected by this turbulence. But here, you've got a much larger conveying portion of the channel that a smaller percentage is affected by the shedding turbulence. The n value does drop. That's what we see. You will not be able to calibrate both of these to the same n value, which means, and we'll talk about this on Thursday, you should not calibrate to one water surface. Because if you calibrate to multiple water surfaces, you will see this effect. So in general, if you're dealing with a single roughness element, increases in flow decrease your n value. Yes?
So, like, do you have a good handle for, like, how much the n
I've
value
always
changes?
wanted to write this paper. In fact, I tried once. I collected 20 of these, 20 models that had n value variation. And I did a little talk about this at a little conference. It's art, not science. I don't. Which is why the best practice is to, and we'll talk about this on Thursday, calibrate to 3 events. Calibrate to a base flow, which is easy. You'll always have a base flow. You can go get it at any time. Calibrate to a bankful flow, which isn't as easy, but not that bad. You have a 50% chance of having bankful flow during your project. And calibrate to a flood flow. And you will generally see this unless something weird happens. Yeah?
So then your default n value, like the ones that are in the tables, should that be your base flow n, your
I like it to be my bankful, but that's because
your bake flow?
my bankful flow. But that's because I'm a sediment transport person, and the whole world revolves around bankful for me. But here's an example. And so you choose a reach. And this is why we don't use the vertical variation n value, because that thing is a beast, and this thing is easy. You choose a reach, because this can be different for different reaches of your river, right? If you've got a mountainous reach, it's going to be different than the sandbed reach. Actually, before I show you this, let me talk about that. Let's say that you have a sandbed river. So your roughness elements are dunes. Now your n value is 0.023. Your flow increases. Is your n value going to increase, decrease, or push? Remember, there's no way to learn something better than to be publicly wrong about it. In this case, this is why that paper is going to be very difficult to write. Increases. And this is, there's no reason you should know this. There's no reason to know this. until you take the sediment transport class. Because what happens with a higher flow is you get higher amplitude bed forms. And so your N value actually increases in these large rivers, until it doesn't, until you get too high and they wipe out, which is why the Missouri is so hard. Yeah.
Have you seen that it's always, the bed form is always proportional in terms of the area that it covers of the conveyance path of the water?
No, in fact, not even close. Not even close. There's one really weird thing that happens though. At some point, you get to a high flow, and then we see the same thing as we saw with temperature, is you go into a new regime, and these plane out. And so on the Cowlitz in the Portland district, when you go from 40,000 to 50,000 CFS, your water surface elevation drops. Okay, yes, I said that right. Let's hear that again. You increase your flow 25%, and your water surface elevation drops because you go from bed forms as your roughness element to a plain bed. You go into a new bed form regime, and you go from an N value of like 0.03 to an N value of 0.022, and it overcompensates for the increase in flow. It's a big deal on that river. And so this ends up being non-monotonic. And so that's one of the reasons why that paper that I want to write and that guidance that you want is so difficult, is that it really is, it gets into my world of what's going on down where you can't see. So how do you do this? Well, once you calibrate to these three water surface elevations and you know what's the trend on your river, you can define the reach, the upstream and the downstream cross section, and then you give it a range of flows. And you choose one flow that will be the kind of the standard. This is what the N values are for. Then, for the other flows, you can give them a ratio. So, in this model, all of the low flows, and this is obviously the Missouri because a low flow is 100,000. All of the low flows are 1. But when the flow increases, the bed forms, in this case, the bed forms are decreasing because it's for the 2019 event where they ran out of sediment. The flow increases, so you want to scale your N value down 15%. And we will linearly interpolate between that and that. And so you can actually, you don't have to run 3 models. You just apply your scaling factor to the reach, and we will decrease or increase your N value based on this relationship. As you saw, these data came in from Mapper. So even though we only have 3 N values, they're showing up as horizontal variation. And that's fine. There's nothing wrong with that. That's a total, if I saw that as a reviewer, I'd just be like, oh, they use good N values, and they brought them in from Mapper. But what you can do, if you want a little bit more control over those, is you can come into tables, and this is a place where I spend a lot of time, is the Manning's N value. These tables actually, I spend a lot of time in all these tables, because you don't want to change these things by cross-section. You want to be thinking about them globally, or at least in terms of reaches. And so I come in here, and one of the things is, this says, these are the edit options for the selected area. For quite a long time, I didn't know that was true, and I didn't think this worked. But I'm going to select the whole area. And actually, this is only going to work for the river and reach I've selected. I could go all rivers, and now it's everything. And then I'm going to select it. And this is cool because if you want to try a higher N value, you can come in here and say, hey, actually, I want these N values to be 10% higher. So I'm going to multiply them by 1.1. But you'll notice that these are all like N value 1, N value 2, N value 3. This button will allow you to reduce to left, channel, and right. Since you only have 3, that's going to work out really well. I'm going to do that. And it says, do you want to do that? And I'm going to say yes. And now you can see that we're in the left bank, channel, right bank framework. And if you go to your cross section, now your N values are in the classic left, channel, right framework. So then, if I want to change all my left or reach of my leftover banks because I want to account for houses. I had them in as blocked obstructions, but I didn't like that. I took them out, and I want to raise all them. Now I can go into that table, and I can say, actually, all of these are going to be 0.08. And that's how you would go and kind of change sections of your N values. The other things that we talked about that you'll want to know is to actually do the horizontal N value, you come on in here, and then it converts you back. And so now let's say that actually this is a parking lot. So everything between that and the channel is actually going to be 0.03. I'm going to come down to 0.814. And I'm going to make that 0.03. I'll apply. And now you can see up there that we have our 0.06, and then we have our parking lot of 0.03, and then we have the rest of our channel. The vertical variation, this is also where you get the K value, which I have used once in my career, and the vertical variation of N value, and I'll just show you that chart. And again, that is very data hungry. Also have only used it once in my career because in general I use tools. This is where you have the seasonal roughness factors if you have, say, macrophytes that grow that make a big difference. But then almost every project I use the flow roughness factors. And so in the flow roughness factors, you're going to choose your river and your reach, your upstream and your downstream affected cross section. And then you'll give it my bankful flow. That's a 1. And then as the flow increases to 20,000, I get a 10% reduction. And as it goes to base flow, I get a 10% increase. And it will linearly interpolate between those values. Oh, you can plot your N values. So when I run my result, and I do this, you can plot your N values, and I do this all the time. This is a place I spend some time. These are the standard plots, and then this is the plot of anything else you want to see. And these standard plots, flow, I look at that all the time, just to look at how the flow is changing through my model. Area all the time, top width. And this N value, the weighted N value, this shows you, and I can go in here, and that's really busy. So I just want to look at my channel for now. And now I can see that there's shenanigans going on here. What this will show you is you can actually look at, right now, I'm looking at all 3 of the profiles. And so you can see that actually the N value of my channel is changing with flow. And so that's a way to represent that and see, along your profile, how is your Manning's N changing and responding to your flow roughness factors. Yeah.